So we defined cosets last time of a subgroup. More precisely, we defined left cosets of a subgroup and gave some examples. By the way, there is a similar notion of right coset, which is defined exactly in a similar manner. Define right cosets similarly, which also plays a role. I mean, if your group is abelian, then of course the left cosets and the right cosets are going to be the same, but if not, then sometimes they may be different. Maybe we'll have some exercise later where we'll see how they're different. So a right coset is a set like this, where you take all the elements of your subgroup H and multiply on the right by A. Okay. And the basic observation that we made from these examples, you can still see a couple of them here, is that once you have a subgroup, you look at these cosets, these left cosets, let's say, then they form a partition of the group. So like here is a cyclic group of order 6, identity a square, a cube, a to the 4th, a to the 5. Identity and a cube together form a subgroup. If you take that subgroup, then that's a coset, this is a coset, and this is a coset. The cosets, there are 3 cosets. Oops. There are 3 cosets, and the group gets partitioned into these 3 cosets. This is what we want to prove, and first thing is to prove this lemma, which gives you 7 equivalent conditions telling you when 2 things are in the same coset. So like this guy, for example, and that guy you see are in the same coset, they're in the same piece. Turns out that the cosets that they make are exactly the same, you see. The coset containing A and the coset containing A to the 4 are exactly the same. So that's like 7. That the coset of one guy and the coset of another guy are the same. The coset containing A and the coset containing B, let's not use of. So the coset containing A and the coset containing B are the same. And there are all these other conditions which are also equivalent. So if you have one of these, you have all 7. And vice versa. So the setup is still that you have a group G and a subgroup H. And you take A and B in G. Then I'm saying that these 7 statements are all equivalent. A inverse B is in H, B inverse A is in H, B is in AH, A is in BH. And you see there's sort of a symmetry going on. They're interchanging A and B. BH is a subset of AH, AH is a subset of BH, and then the 7th one is AH is equal to BH. And you can check, for example, what is one saying? A inverse B is in H. Like this guy and that guy are in the same coset. So the inverse of the first guy times the second guy, which happens to be A cube. Is that in the subgroup H? Well, yes, it is. So that's one of the conditions that determine when 2 things are in the same coset. That's why A square and A to the 5 are in the same part. So it's saying that sort of thing. So you can check all these 7 conditions against the examples we gave, but the arguments are rather simple anyway, and I won't write complete details, but let's just write a little bit. Why is 1 and 2 equivalent? 1 implies 2, let's say. Well, what you notice is that the inverse of A inverse B is, when you take inverse, you switch the order and put inverses. So it's B inverse times the inverse of A inverse, which is B inverse times A. So you see the inverse of this guy is that guy, and the inverse of that guy then would be this guy. So they are inverses of each other. So if one of them is in H, the inverse is also in H, and vice versa, because H is a subgroup. So if H contains something, it also contains the inverse. That's why 1 and 2 are equivalent, because one of these elements is the inverse of the other. All right. What about 1 implies 3? Well, suppose A inverse B is in H. What does that mean? That means A inverse B is some H for some little h in capital H. But that means B is A times H if you take this equation and multiply on the left by A. But A times H is exactly what an element of A capital H looks like. So B is in AH, and that's what this is saying. So that's why 1 implies 3. The argument for 3 implies 1 is exactly similar. So this I'll say similar. You can write it out. So I get 1 and 3 are equivalent. The equivalence between 2 and 4 are exactly the same argument. The equivalence between 1 and 3 and the equivalence between 2 and 4 are exactly similar. That's why I wrote the statements like this. Let's see 3 and 5. Well, B is in AH. That's what we are assuming. Now, I want to go this way. If B is in AH, this means B is A times some element of H for some H in H. Now, a typical thing in B times H looks like, so take some X in B times capital H. Then this X is B times some element of capital H for some K in capital H. So X is B times K, but B is A times H, so A times H times K. And both H and K came from capital H, so this thing is still in capital H, H times K. So this is in AH. So what did we get? We took something in BH, we saw that it's in AH. So that's why BH is a subset of AH. That's this implication. And the other implication is very straightforward, of course. B is certainly in BH because B is B times E. So B is in BH, and if BH is a subset of AH, then B is also in AH. That's the other implication. So you get 3 and 5 are equivalent. The equivalence of 4 and 6 is exactly the same thing. Now I know that 1, 2, 3, 4, 5, 6 are all equivalent. So if you assume 5, let's check 5 implies 7. Assume 5. By what we have proved so far, 5 implies 6. So if 5 is true, then 5 is true and 6 is true. But 5 and 6 just say that BH is a subset of AH and AH is a subset of BH, so the sets are the same. That's why 5 implies 7. Same argument tells you 6 implies 7. And then 7, of course, gives you the other one. 7 is stronger than 5 and 6, of course, because if the sets are equal, then they are subsets of each other. Okay? So that's why these 7 statements are all equivalent. And once you know that, you get this fact. So here is a definition. Then you get, quite quickly, that being in the same coset defines an equivalence relation on the group. The relation of being in the same coset is an equivalence relation on the group. And once you have an equivalence relation, you know that the equivalence classes are going to form a partition. And these equivalence classes for this relation are what? They are the cosets. So hence the cosets form a partition of the group. But let me write something down. The setup is still the same. Given a subgroup H of a group G, we say A is congruent to B mod H if any of these conditions, any of these 7 conditions hold. Let me just write the first one, or the last one maybe. Let me write the first one, A inverse B in H. So i.e. any of these 7 conditions hold. If one of them hold, then all of them hold. So all of them hold, actually. All right. By the way, I should mention that in the book, they use right cosets. So what they call congruence is slightly different because they are talking about right cosets. We are talking about left cosets. It's a minor difference. I mean, you might as well develop the theory for the right cosets. It's exactly a parallel theory. All right. So this gives you a relation, right? This gives you a relation on the group G. So we say, maybe we write down, R is all pairs in the group such that A is congruent to B mod H. Then R is a relation on G. I claim, so two elements A and B in G are related via R if and only if A and B are in the same coset, left coset. And I claim that from these 7 conditions you can easily check that this is an equivalence relation. Verify that R is an equivalence relation. All the work has already been done in proving that lemma on G, and the equivalence classes. What are those? You give me a guy, the equivalence class of that guy is all the things that are related to it. All the things that are related to it are exactly the guys that are in the same coset. So an equivalence class of a guy is exactly the coset that contains that guy. And the equivalence classes are exactly the left cosets. So the left cosets form a partition of G. In particular, 2 different left cosets are disjoint, and so 2 left cosets are identical or disjoint, and the left cosets form a partition of G. And the Lagrange's theorem just follows from this immediately. Let me still verify why this is an equivalence relation. So remember, one has to check 3 things. That A is related to A. That just says A and A are in the same coset. If you use the condition 7, it's the simplest, I think. It's just saying AH equals AH. Of course, true. The second one is saying that if A is congruent to B mod H, then B is congruent to A mod H. Again, if you use this condition 7, then it's automatic. Both are equivalent to saying AH equals BH. And the third says that if A is congruent to B mod H and B is congruent to C mod H, then A is congruent to C mod H. And again, if you can use condition 7, it's immediate. Yeah. So the verification of equivalence relation is very straightforward, and we know by general result about equivalence relation that whenever you have an equivalence relation on a set, the equivalence classes form a partition of the set. And the equivalence classes in question are exactly the left cosets. Okay. We'll write down Lagrange's theorem next time and get a couple of consequences.